Alright guys, we're going to review graphing and solving root equations, but before we do that I'm going to remind you of the parent functions for both square root and cube root functions. So for square root functions, y equals the square root of x. Remember that the table for that function is 0, 0, 1, 1, 4, 2, 9, 3. You can keep going. 16, 4, 25, 5, 36, 6. But your perfect squares are in the x column, and then the square root of those numbers is in the y column. And what that looks like if we graph it is the point 0, 0, 1, 1, 4, 2, and 9, 3. It looks like that curve right there. That's a square root function, and that is the parent function for square roots. And this table is the table of values for the parent function. So when we start to transform the square root function, we are using this as our starting graph, and we'll transform it according to our transformations in the function we're given. All right, cube root functions. Cube root functions look like this. Y equals the cubed root of x. And remember that the table for those functions is -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. And again, the x column is perfect cubes, and the y column is the cubed root of those numbers. And what that looks like graphed, -8, -2, -1, -1, 0, 0, 1, 1, 8, 2, looks like this. And so anytime we're transforming a cube root function, we are taking this function and moving it around or stretching it or shrinking it. All right, let's look at the review. The first set of problems on the review is this table where you're asked to find a transformation or write an equation and then provide a graph, a table, and a domain and range. Our first equation right here is y equals the square root of x plus 2 minus 4. Remember that the formula for a square root function is a times the square root of x minus h plus k, right? And we remember that a is vertical stretches and shrinks, h is movement left and right, and k is movement up and down. In this case, we don't have an a value. It's 1, which is our standard multiplier there. But we do have a h value and a k value. What we have to remember about h is that it lies. So even though it says plus 2, that 2 is going to move the graph left. And then the minus 4 is going to move the graph down. So this is a standard square root function that has been moved left 2 and down 4. I'm going to zoom in on the graph so that you guys can see it. Oops, sorry, wrong way. So you guys can see it more easily. Remember that when we transform the function, we're starting with this graph right here, and we're transforming it. So we're going to go left 2 and down 4. So I start with that 0, 0 point right there, and I move it left 2 and down 4. It's this point right here. And then I come to the 1, 1 point, and I go here and then move it left 2 and down 4. And then the 4, 2 point, we move left 2 and down 4. And the 9, 3 point, again left 2 and down 4. And so that moves the entire graph left 2 units and down 4 units. Make sure that you connect those dots, that you do not continue beyond this point, and that you make sure to put an arrow at the end there. Now the table of values, you can either get that from your calculator, having graphed this equation in your calculator and looked at the table, or you can pull them from this graph right here. So x and y. And then I'm going to start over here. This is the point -2, -4. I have the point -1, -3. The point 2, -2, and the point 7, -1. And so those are the table of values for the square root function that has been moved left 2 and down 4. And then domain and range. Remember that the domain and range of the parent function is 0 to infinity. This function has been moved left 2, so that domain is going to be moved left 2 as well, so -2 to infinity. And this function has been moved down 4, so that range value 0 to infinity has also been moved down 4, so it's -4 to infinity. All right, the next problem, they gave us a verbal description but not an equation, and that's fine. They said the parent function is the square root of x, has a vertical stretch of 3, is reflected across the x-axis, and is translated 1 unit left and 3 units down. And so we need to go through here and identify, are we talking about a, h, or k, and how do we put that together? This vertical stretch of 3 is an a value, right? Stretches and shrinks are a values, as is the reflection. That means it's a negative a. 1 unit left is an h value, and 3 units down is a k value. And so if we take all those numbers and put them together, what we end up with is y equals, reflection is negative, a vertical stretch of 3, so -3, square root of 1 unit left, which means we're going to say x, and we're moving left, which should be minus, but remember h lies, so it's x plus 1, and then 3 units down, so it's -3. And so that's our function. Y equals -3 times the square root of x plus 1 minus 3. Now, we do the same thing that we did. Now, you can certainly plug this into a calculator and look at the table and plot the points. That is totally fine. We are going to transform it based on our parent function. So I am going to move the points first, and then we'll deal with the vertical stretches and shrinks. So this is moving left 1 unit and down 3 units. So I take that point 0, 0, and I move left 1 and down 3, and that puts this point right here. And then it's 0, 0, so reflection and stretches and shrinks do not have any bearing on that point. So that point stays right there, -1, -3. This point right here, 1, 1, if we reflect it, it goes underneath the x-axis, so it ends up here at 1, -1. And if we stretch it 3 units, instead of it being -1, it's 1, -3. And then you move it left 1 and down 3. And so that point goes there. The point 4, 2, if you reflect it, it comes down to -2. And if you stretch that 2 by 3, you say 2 times 3, that takes you down to -6, and then move it left 1 and down 3 more, which takes you down to -9. Now, if you followed that, great. And if you did not, that is okay. Throw it in the calculator, look at the table, all right, and your graph should look like this. So guys, we're going to connect these dots. Remember that this is like our anchor point, it's our starting point, and then we go from there. Your graph should look like my graph. It should start at the -1, -3, and it should have an arrow on the other end. It should curve, okay, and it should be kind of a steep curve because there's a distance of 3 between these points. Instead of up here, we see that there's a distance of 1 and then a distance of 1. All right, guys, to make the table for this graph, just pull the points from your graph right here or from the calculator. So our points are -1, -3, 0, -6, and 3, -9. And those are all the points that fit on the graph. It's okay if those are all the points that are in your table. You should feel free to include more points if you can. All right, and then domain and range. So remember that the domain for this function, parent function, is 0 to infinity. Here we've moved it left 1, so my domain is -1 to infinity. And remember that your range for the parent function is 0 to infinity as well. In this case, we've reflected it. So instead of starting at 0, we're going to start at -infinity. So my range is -infinity to my top y value, which is -3, right there. And because reflections start at -infinity for range when we're talking about square root values. All right, guys, the next problem is a cube root function. And remember that that means we're going to be using this information right here, and we're going to be modifying it. But this is our parent function. So it's a cube root, and I know that because of the 3 right here. The transformation formula for cube root functions is the same as the transformation function formula for square root functions. It's y equals a times the cubed root of x minus h plus k. And so we're looking at a function that is, again, has an h value and a k value. Remember that h lies, so this is the -2, but that means it moves right 2. And then the +1 means it moves up 1. And then let's talk about graphing. So again, I go back to my parent function. And remember, guys, if you want to compare your parent function, you have a notes page that has, you've got a notes page for square roots and a notes page for cube roots, and it's got the parent function at the very top of the page. All right, so my function that's going to go here has been moved right 2 and up 1. I'm going to take these points and move them right 2 and up 1. So I'll start at -8. So -8, -2, and I'm going to move right 2 and up 1. And we end up here at -6, -1. If I take the point -1, -1, and I move it right 2 and up 1, we end up at 1, 0. If I take the point 0, 0, and move it right 2 and up 1, we end up at 2, 1. If I take the point 1, 1 and move it right 2 and up 1, we end up there. And if I take 8, 2 and move it right 2 and up 1, we end up at 10, 3. All right, connect those points as best you can. This is a teeny tiny graph, but you want to make sure that you try to get those curves on there. And then when you make your table, remember you can get those points from the calculator or you can pull them from your graph. So just, the points that we graphed. This is -6, -1, 1, 0, 2, 1, 3, 3. I'm sorry, that's a 3, 2. It's a tiny graph. And then 10, 3. Now, domain and range for this is very easy because domain and range of all cube root functions is -infinity to infinity. And everybody is going to get all of those points on the test tomorrow because we are not going to forget that the domain and range for every cube root function is -infinity to +infinity. All right, the second cube root function again gives us a verbal description instead of a formula. That is okay. We've got a cube root that has a vertical compression of 1/2 and is translated 2 units right and 3 units up. So vertical compression of 1/2, that's your A. 2 units right, that's your H. And 3 units up, that's your K. And so we write this, I'm going to write it diagonally so I have more space. It's y equals 1/2 the cubed root of, remember that we're moving 2 units right, but h lies, so it's x minus 2, and then up 3 is plus 3. That's our cube root function right there. And when we go to graph it, again, we're going to come back to the parent function, although you are certainly welcome to put this into y equals and pull up the table and use the table to graph it. I am going to go back to my parent function right here. And I'm going to use these points. So I will start with the point 0, 0 in this case just because we're multiplying by 1/2. So the point 0, 0 moves right 2 and up 1, 2, 3. And that vertical compression of 1/2 does not affect that point. Now, the point 1, 1, when we move that point, right 2 and up 1, 2, 3. The vertical compression there brings it down to 1/2. So usually it is 1 unit above the center point, this 0, 0. It's usually 1 unit above. A vertical compression of 1/2 means instead of being 1 unit above 0, 0, it's going to be 1/2 unit above. And the same thing goes here. Instead of being 1 unit below 0, 0, it's going to be 1/2 unit. So we're going to be going through the 1/2 point. All right, so we're right there, halfway between, it's 3 and 4, right there. It's 1/2 unit above that center point. And then this point right here, the 8, 2, again, it is 2 units above 0, 0. So when we half it, it's only going to be 1 unit above 0, 0. And that point moves, again, right 2. So it's 8, 2, moves right 2 and up 1, 2, 3. But because we're halving it, it ends up right here. So we would start at 8, 1, move right 2 and up 1, 2, 3. We end up here. Ooh, there. It's a tiny bit. All right, same thing goes for these points over here. This point is 1/2 a unit below our center point 0, 0. So we're instead of starting at -1, we're going to start at 1/2. And so we start here at -1, -1/2, and we move right 2 and up 1, 2, 3, right there. And so it's again, it's a 1/2 a unit between 2 and 3. That one is. And then if we come over here to 8, -2, we are halving the y value. So we'll start at 8, -1, and move right 2 and up 1, 2, 3, right here. And when you connect those, and again, this is a very small space we're talking about. It's really hard to get that curve, but that's what that looks like. Make sure you've got a little bit of a curve there. All right. For our table of values, again, you can use the table in your calculator, but you can also just use the values we have. So this point right here is at -6, 2. This point right here is at 1, and that's a 2.5, so 2.5. The middle point ends up at 2, 3. This point immediately to the right ends up at 3 and 3.5. And then the point that would be 8, 2 ends up at 10, 4. That's a 4. All right. Notice that there's a distance of 1 between these 2 points, 2 and 3, and a distance of 1 between the 3 and the 4. All right, guys, domain and range is the easiest part of any cube root function because it's always the same answer. Domain is -∞ to infinity, and range is -∞ to infinity. You should look for that on the test first and fill it out first because you know you're going to get the right answer. All right, guys, let's talk about solving. So these first equations are square root equations. And what we're going to do is we're going to first identify where the square root ends. Right here, there's only an x and a 2 under the square root. And so I can rewrite this as x minus 2 to the 1/2 power is equal to 5. Because this parenthesis set is alone, there's nothing in front of it, we're not adding or subtracting anything to the end of it. We are good to just square both sides and get rid of it. So this is x minus 2 to the 1/2 squared is equal to 5 squared. And what happens is these two exponents cancel each other out, and we end up with x minus 2 on the left side of the equation and 25 on the right. To solve for x, you're going to add 2 to both sides. You get x is equal to 27. We have to make sure that we check our answer because square root equations can have extraneous solutions. So make sure you plug it back in. Square root of 27 minus 2 is equal to 5. It's the square root of 25 is equal to 5. And in fact, 5 is equal to 5, so this checks out, and that is the correct answer to that equation. For the second problem, guys, Again, identify where the square root ends. The 4x and the 1 are under the square root. Nothing else is. And so when I rewrite this, I'm going to put the 4x plus 1 in parentheses with a 1/2 exponent and leave the 3 and the 2 out. And what that means is that I've got to solve for this parenthesis set. I can't just square both sides. I've got to solve for the parenthesis set. First thing I'm going to do is move the 2, and you have to move the 2 first. So this is 3, and then 4x plus 1 to the 1/2 is equal to 9. And that 3 is still in my way. I need this parenthesis set completely alone, like the one in problem 1. And so I'm going to get rid of the 3 by dividing both sides by 3. And you get 4x plus 1 to the 1/2 is equal to 3. And now the parenthesis set is alone, so I can square both sides to get that 4x plus 1 out. So I'm going to go ahead and do that. Square them, and remember those two exponents cancel out. So I get 4x plus 1 is equal to 9. We're not done. X is not alone, and so we still have to solve. We do that by subtracting 1 from both sides. You get 4x is equal to 8, and then divide both sides by 4. And what we get is x is equal to 2. Now remember, it is very important for you to check your answers. So we're going to do that and make sure that 2 works. This is 3 times the square root of 4 times 2 plus 1 plus 2 is equal to 11. And we've got to do this in the right order. So the right order is underneath the square root first. So this is 3 times the square root of 4 times 2 is 8 plus 1, and then plus 2 is equal to 11. So 3 times the square root of 9 plus 2 is equal to 11. And so now we've taken care of the square root. What is the square root of 9? It is 3. So this is 3 times 3 plus 2 is equal to 11. Multiplication, 9, and then plus 2 is equal to 11. And what you get is 11 equals 11. That works. And so this is the correct answer to that problem.